Hello, and welcome to this presentation, Getting Started with the HMC8015 Power Analyzer. In this presentation, we'll show how to use the Rohde Schwarz HMC8015 Power Analyzer to perform a wide variety of power-related measurements, including power factor, inrush current, standby power, and harmonics measurements. This presentation assumes a basic familiarity with electrical power measurements, but separate technology presentations are available if you're unfamiliar with or would like a brief review of these power-related topics. Let's start with an instrument overview. The Rohde Schwarz HMC8015 is a standalone compact benchtop analyzer that's used to measure and characterize both AC and DC power from 15 microwatts to 12 kilowatts. The HMC supports both numeric and graphical displays of 26 key measurements, as well as advanced analysis functions such as waveform view, inrush current characterization, harmonic analysis, etc. The instrument can be directly controlled via a simple and intuitive user interface, but can also be accessed and controlled remotely. Measurement data is logged and exported in easy-to-process CSV files. The HMC8015 can also perform automated conformance testing and report generation for verifying compliance to standby power and harmonic standards. The first step in using the HMC is connecting to the device under test, or DUT. This can be done directly using the 4mm safety jacks on the front panel. Voltages are measured using the red V jack, currents are measured using the blue A jack, and the black COM jack acts as the shared measuring input for both voltage and current measurements. As indicated on the front panel, the HMC can measure up to 600 volts RMS and 20 amperes RMS, although the current range can be significantly extended using an external current clamp or shunt. Note that for safety purposes and to avoid instrument damage, the HMC will automatically shut down if these limits are exceeded. In many cases, the connection to the device under test is made by means of an AC mains adapter, such as the HZC815. The DUT is plugged into the adapter, and then color-coded cables connect the AC plug contacts to the appropriate plugs on the HMC. Different versions of the HZC815 are available to support the different AC outlet types found in different regions of the world. Next, we'll cover basic navigation and configuration of the HMC using the front panel controls. A set of 4 soft keys are provided for menu navigation and parameter configuration. Each button corresponds to the menu item shown to its left. There's also a back or escape button, which is used to exit or close menu items, as well as to dismiss dialogues or messages. Although the HMC can automatically set voltage and current ranges, manual configuration of these ranges is also possible through the front panel U and I keys. Numeric values can be entered and/or modified in 2 ways. The Shift key activates the numeric keypad for entering values, and the rotary knob and cursors can be used to both select menu items as well as to modify numeric parameters. 2 important keys for configuring measurements are the Data Acquisition menu button and the Measurement Configuration button. Both of these menus and their functions will be described in detail later in this presentation. 2 additional helpful keys are the Hold key, which pauses the update of measured values, and the Reset key, which resets or restarts a running measurement. Administrative functions are also accessed via the front panel controls. The Setup key is used to configure instrument setup, such as controlling screen brightness, assigning addresses to interfaces, etc. The Save Recall key is used to save and load instrument configurations, and holding this key down can be used to take a screenshot. The HMC also has an integrated help function accessible via the Help hard key. The first step in making measurements with the HMC is selecting the measurement mode, which is selected using the View hard key. The 5 different measurement modes are Numeric mode, Waveform mode, Trendchart mode, Inrush mode, and Harmonics mode. Let's look at each of these modes in more detail and explain how they're configured and used, starting with Numeric mode. Numeric mode is the default display mode and provides continuously updated or instantaneous numeric values of measured parameters. Due to the large number of measurements supported by the HMC, these values are presented in 4 screens. The number keys on the right can be used to move between the measurement screens. Note, too, that each screen can display either 6 values, as shown above, or 10 values, as shown below. Pressing the number key twice is used to toggle between the displays. It's also worth noting that the top of the screen also shows important configuration parameters, such as the voltage and current measuring ranges, the operating mode, AC or DC, the elapsed measurement time, whether logging has been enabled, and the selected remote access method and status. Let's look at some of the numeric mode measurements. On the first screen, we have the instantaneous RMS values of voltage and current, as well as active, apparent, and reactive power and power factor. The voltage and current ranges, here 300 volts and 1 amp, are displayed as bar charts showing the instantaneous values as a function of range. On screen 2, we have the average, positive peak, and negative peak values for both voltage and current, the frequency of voltage and current, and the total harmonic distortion of voltage and current. In numeric and other modes, the acquisition button provides access to various measurement parameters. The voltage and current buttons can be used to set the range and enable or disable auto-ranging, and crest factor can be increased if needed to measure signals with large spikes. Mode is primarily used to choose whether measurements are made on AC or DC. The HMC can also determine this automatically. Additional mode parameters can be adjusted if necessary, but in most cases the default values are sufficient. The peak hold button can be used to activate the peak hold or to reset the peak hold period. And finally, the refresh rate can be changed from its default of 10 values per second to a single average value every second. The next mode we'll look at is Waveform mode. This mode provides a graphical view of voltage, current, and/or power over one waveform period, similar to how these would be displayed on an oscilloscope. The period is automatically determined by the HMC. An automatic hardware-based trigger is used to start each acquisition, and the waveform is continuously updated. Vertical scaling of the waveform can be done using the I and U keys on the front panel. In addition to displaying the waveform, the HMC also provides numerical results for RMS voltage, RMS current, and power, with soft keys being used to choose which traces to display or hide. Let's use Waveform mode to compare a traditional 60-watt incandescent light bulb with a 60-watt equivalent LED bulb. On the left, we see that current, voltage, and power are all in phase for the almost entirely resistive 60-watt incandescent bulb. But on the right, we see that the LED bulb draws current, the red trace, in a nonlinear fashion, which also causes power, the green trace, to be nonlinear as well. We can use the numeric power results to see that the incandescent bulb consumes about 6 times more power than the LED. 60 watts are being consumed by the incandescent versus just 9.5 watts by the LED. Trendchart is another graphical mode which allows up to 2 measured values to be plotted as a function of time, in a way similar to roll mode on oscilloscopes. Trendchart mode is used to look at longer periods of time. 40 seconds to 80 minutes of data can be shown on the screen. The user selects which values to plot and the time base, but the vertical trace scaling is handled automatically. While running, the max and min values are displayed numerically on the top and bottom of the screen, and the clear button can be used to start a new acquisition or to clear results. Let's look at two examples of Trendchart mode results. In the first example, we see that voltage, the red trace, drops when current, the blue trace, increases. In the second example, we're looking at current and the total harmonic distortion of current, and we can see an inverse relationship. Total harmonic distortion decreases when the current increases. Compared to Trendchart mode, Inrush mode is concerned with much shorter events. This is because inrush current is defined as the current that's drawn when a device first powers up or is switched on. This current can be very high compared to the current drawn during steady-state operation. There are two ways of measuring inrush current with the HMC. The first of these is using peak hold while in numeric mode. The second is in inrush mode. In inrush mode, the voltage and/or current are plotted following a trigger event. This is similar to making a single-shot capture on an oscilloscope. In addition to plotting these values, Inrush mode also numerically displays maximum values of voltage and current during the acquisition time. Inrush mode measurements do not run until a trigger event occurs, and this trigger must first be armed using Activate On. The trigger must then be rearmed after each measurement. Settings include the acquisition time from 16 milliseconds to 67 seconds, the trigger source, which can be voltage or current, but is usually current, the trigger slope, rising or falling, and the trigger level in either volts or amps. Note that the Inrush waveform data can also be exported in CSV format. Here are a couple of examples of Inrush mode. In the first example, we see that the current has an initial peak of about 1 amp before stabilizing at a lower level. Whereas in the second example, the device under test draws more current with each voltage cycle. The last standard measurement mode we'll look at is Harmonics mode. Harmonics are created by nonlinear loads and can create many problems in the power grid. Harmonic mode performs an FFT, or fast Fourier transform, in order to calculate the RMS value and phase angle of up to the first 50 harmonics. It's also possible to display only the odd or even harmonics. The cursors or rotary knob can be used to view the values for an individual harmonic, highlighted in yellow. In addition to the bar chart shown here, harmonics can also be viewed in table form, showing per harmonic magnitude and phase. The bar chart display is useful in visualizing patterns, such as the much higher amplitude of odd harmonics compared to even harmonics in this example. Bar chart mode only shows amplitude, so tabular mode is needed if we want to see the phase angle in degrees for each individual harmonic. Next, let's spend a few minutes briefly looking at some additional features of the HMC. These include the energy meter or integrator function, limit testing, external inputs and outputs, the use of external sensors, data logging, and remote access or control. The energy counter or integrator is a special numeric mode configured from the Measure menu, and this calculates and displays the cumulative power or energy consumption of a DUT over time. This can be helpful in determining the energy cost of a device in both active and in standby operation. The HMC calculates the energy consumption over time and reports the results in positive, negative, and total watt-hours, updated in real time. These results can also be logged to a file and exported for documentation or for further analysis. Another numeric mode function is limit testing, which is configured via the Measure hard key. Limits monitor whether a measured value, such as current, power factor, etc., stays within user-specified limits. Up to 6 sets of limits can be defined, where each limit has a high and low value for the measured parameter. Limit results are displayed in two ways, both as a percentage of the limit range and as a bar graph relative to that range. For example, the RMS current limits are defined here as 0 to 400 milliamps, so a limit value of 83.8% corresponds to a measured value of 335.2 milliamps. Limit violations can also be externally signaled using the digital output connector on the rear panel. The rear panel of the HMC8015 has 4 BNC connectors that can be used for interfacing with other test instruments or for automation. The analog in connector measures an external voltage input and displays this value in numeric mode. The analog out connector produces a voltage which maps to a user-selected measurement value on the HMC. For example, voltage, current, or percentage of limit value, as described just a moment ago. The digital in connector can be configured to display whether the input is high or low, or the frequency or duty cycle of an external pulse width modulated signal. And digital out can be used to either indicate a passing or failing limit value, or it can output the measurement frequency in the form of a square wave. The external hard key is used to configure the behavior of these inputs and outputs. The external hard key is also used to configure external sensors. An external clamp-style current probe or a differential voltage probe can be connected to the sensor jacks on the front panel of the HMC. These probes can be used to extend the current measurement range from 20 amps up to 1000 amps. Configuration parameters for external sensors include the type of sensor, either a clamp-style current probe or a differential voltage measurement being used to measure current through a shunt resistor, the clamp probe scaling value or shunt resistor value, and the measured voltage range. Next, let's talk about data logging. Measured data can be logged in the form of a CSV or comma-separated value file. Up to 10 user-defined measurement values can be logged, and logging rate can be configured up to a maximum of 10 measurements per second. Logging can be controlled in 3 different ways. It can be manually started and stopped. The user can specify a given number of measurements to make, or the absolute start and stop times or durations can be configured. The maximum logging duration is 96 hours, and the log CSV data can be easily saved to or exported via an attached USB drive. It's also possible to remotely access or remotely control the HMC8015 via its external interfaces located on the rear panel. LAN and USB interfaces are standard, and there's an optional GPIB interface. One method of remote control is using the free HME Explorer Power software module, which provides both graphic and numerical views. Another method is using industry-standard Skippy commands to configure the instrument, start measurements, and retrieve measurement results. Please see the documentation on these tools to learn more about their capabilities and how to use them. The HMC optionally supports automated measurements for testing compliance to 3 important power standards, IEC 62301 and EN 50564, which measure energy consumption in low power or standby mode, and EIC 61032, which verifies the level of harmonic currents. These compliance tests are implemented as menu-based step-by-step wizards, which prompt the user for parameters and test configuration. The tests run automatically, and results can be displayed on the screen in tabular form and can also be saved and exported in HTML format. Compliance tests are accessed by pressing the Measure Hard key, selecting Standards from the menu, and then selecting the standard to test against. Let's now show how the wizard is used to configure a compliance test. Here we'll look at EN 50564. First, the region and voltage current are selected, and then the user is prompted for the expected crest factor and max current. This test also requires that the pattern of power consumption, static, variable, or cyclic, also be specified. A connection diagram is shown, and then the user is prompted to start the test. Measurement results are displayed in real time as the test is running, and both elapsed time and total test time are also displayed. At the end of the test, a pass-fail result is given. Any measured values which fall outside of the specified range are displayed in yellow. The measurements can then be restarted, or results can be exported to a USB drive in HTML format by selecting Save HTML from the menu. Let's end with a brief summary. The Rohde Schwarz HMC8015 Power Analyzer can be used to make a wide range of power-related measurements using 5 different measurement modes: Numeric, Waveform, Trendchart, Inrush, and Harmonic. Each of these modes has user-specified configuration and measurement parameters that are entered and adjusted through the HMC's simple user interface. Additional useful functions for power measurements include a power integrator, limit testing, external input and output connectors, and data logging. In addition to the front panel interface, the HMC also supports remote access and control using either the HME Explorer software application or industry-standard Skippy commands. Finally, optional automated conformance tests are available for verifying compliance to various international standards for standby power and current harmonics. This concludes our presentation, getting started with the HMC8015 Power Analyzer. If you'd like to learn more about the HMC8015, power analysis, or other power measurement-related topics, please see the links in the video description. Thanks for watching.